Alright, so here we've got some more polynomials, and this is sort of talking more about modeling and thinking about, like, what does the math tell you about the situation. So we've got Noah cutting a piece of paper or a piece of cardboard, cutting squares out of each of the corners, and then you can fold it up and make an open top box. Okay, and so all the squares have the same side length of x, and he drew this graph where x goes between -1 and 5. And I want you to think, what does it mean? What does x mean in this problem? So let's look back at x. X is the length of the cutout squares. Okay, so does it make sense to cut out a square with a length of -1? I don't even know what that means. Maybe you're taping extra paper onto the box. That doesn't work. Does it make sense to cut out a square of 5? Well, I don't know, because I see this part of the graph right here where it dips down into the negative. What does the y value mean? Well, the y value in this problem is the volume. Does it make sense to have a negative volume? No. And then it zips back up to positive. Well, we can't have our volume become negative and then become positive again. None of this part here is meaningful, because what's happening is if we cut out too much of our box, like if we tried to make x bigger than this halfway point here, we would cut like this, and then we'd also have to cut from this side. You can't have two overlapping cuts. So it doesn't make any sense to cut an x that is more than halfway across the paper. Okay? So let's get rid of some of my scribbles here. What is an appropriate domain? When you read appropriate domain, it just means what x values make sense. So it looks like from 0 to about 2.5. I'm using less than instead of less than or equal to because it doesn't make sense to cut out exactly 0. You need to cut a little bit if you're going to fold it up to make a box. And it doesn't make sense to cut exactly 2.5 either, because then you would just cut like your paper would split in half. What is the approximate maximum volume? Just eyeballing it, it looks like it's at 1, 15. And so that would mean that if you cut out 1 inch squares, then you'd get 15 cubic inches. I guess I should double check that the problem was in inches. Yeah, cubic inches. Okay. Now this problem is very similar. It's just another problem with the same open box, but now our friend Tyler, graphed it between -1 and 7. So we're just going to, without so much discussion, I'm just going to say the domain is 0, less than x, less than 3.5. Maximum volume of the box is whatever that highest y value is. 55, I guess. It looks, it's like, it's a little bit above 50. I'm just going to go with 55 because I don't have a more precise way to do it. 55, whatever's units squared. So what are the units here? Come on. Cubic inches again. Alright, there we go. Alright, moving on. Which polynomial function's graph is shown here? Well, if I look at the graph, I see that I've got a -4, a -1, and a +3 as x-intercepts. So I should see an x plus 4, an x plus 1, and an x minus 3 as factors. And that is, I guess, option B, written in a little different order. The order doesn't matter because if you multiply numbers in a different order, you get the same answer. All right, scooting on down. Number 11, degree and end behavior here. All right, the degree is, I almost missed this one. The degree is 4. I was looking right here, but then I noticed that this has a higher power. The degree is 4. The leading coefficient is 2, which is positive. I know that even degrees look like this or like this. I know they look like this for positive leading coefficients. They look like that for negative leading coefficients. So this is the one. You should have that in your notes. You don't have to memorize those 4 different possibilities of positive, even, and negative, odd, and all that. But you should be able to just like work through the process. Like, okay, what's the degree? What's the leading coefficient? Is it even or odd? Is it positive or negative? What's the situation? So this picture right here just means as x goes to the right, so does y. And as x goes to the left, goes to negative infinity, y goes to negative infinity. If you want to write it out verbally, you can say that whole nasty sentence that the textbook says as x gets larger and larger in the positive direction, y gets larger and larger in the positive direction. All right, let's see how we're doing on time here. We're doing great. All right, so sketch a graph of the following equations. So I know that this is going to have an x-intercept at -1 and at +4. So let's put a dot at -1 and let's put a dot at +4. 1, 2, 3, 4. I know that this has a degree of 3. Its leading coefficient is 1, so it's odd positive. So it's going to look like this. I know also that there's a squared on -1, so it's going to bounce and go through like that. All right, next one. I see we've got x equals 3, -1, and 2/7. If you don't see 2/7 off the top of your head, just set your equation equal to 0. Add 2 to both sides. Divide by 7 on both sides. You get x equals 2/7. That's somewhere here. It's hard for me to get super accurate. 2/7 is pretty close to 0. And then here's 1, 2, 3. Here's -1. Again, degree is 3. Leading coefficient is 7. It's positive, so it's that same odd positive shape for the end behavior. But there's no bouncing here, so it just goes through, through, through. We only have to worry about bouncing when we see a power on one of our factors. If all our factors have a power of 1, you're just crossing through all of them normally. All right, what do we see here? Here's our graph. This looks just like what I was talking about, that same shape. So we know our degree is odd. We know our leading coefficient is positive. And we also know that the y-intercept is positive. I haven't said this in this video, but the y-intercept is the same as the constant. So we have odd, positive, positive. Okay, scooting on down. All points of intersection. I think we're actually at a good place. Okay, I'll pick up with this one on the next video.